Hello there. In this lesson, we're going to learn about electron shells and subshells within the quantum atomic model of the atom. And so we're going to combine what you already know a little bit about from your Bohr-Rutherford diagrams, which is still part of the quantum atomic model, and add to it some of those wave patterns that you learned about in the previous lesson. So the different wave patterns are called subshells, and as you go further from the nucleus, there's space for more subshells or more wave patterns and possible energies for our electrons. All right, so let's get started. So there are four numbers used to describe different properties of the quantum mechanical wave features of an electron. So 1, 2, 3, 4. The first two we're going to look at in this lesson, which are called shell and subshell, and the second two we'll learn about in the following lesson called orbital and spin. So yes, shell and subshell, here we go. So the first number, called the principal quantum number, principal means first, it's given the symbol n, and it describes those areas of space where electrons can exist around an atom. So just like your Bohr-Rutherford model of the atom, there are kind of like onion layers of electrons around it. Not planets around the sun per se, but still areas of space where those electron wave patterns can be. And the number of electrons that can go into each of those layers can be determined from the equation 2n squared, where n is the number of the layer. So layer number 1 here would have 2 times 1 squared. 1 squared is 1 times 2 is 2. So 2 electrons in that first layer. And then you go to layer number 2, and you'll have 2 times 2 squared. 2 squared is 4, times 2 is 8. And then layer 3 out here is going to have 2 times 3 squared. So 3 squared is 9, times 2 is 18. And the fourth shell is going to have 2 times 4 squared, which is, what is that? 4 squared is 16, 32. And then we're going to go to the fifth level here. And it has 5 squared, which is 25, times 2, which is 50 electrons. And then we are going to finish off here in the sixth layer. 6 squared is 36, times 2 is 72 electrons in that outer layer. And there's not too many atoms that have electrons way out there, so most of our attention is going to be focused on these first four. All right, quantum number 2. Quantum number 2 is called the secondary quantum number, and it is given a symbol of a scripted L, like that. And it describes the different energies of electron that are possible within a shell. So not all of those electrons that we listed on the previous page have the same energy. They'll have different energies. And as we discussed with our quantum introduction, different energies means different wave patterns and different probabilities of finding electrons in different places. And so each shell on the quantum model, here's shell, will have different subshells that are possible within it. The number of subshells corresponds to the number of the shell. So shell is the symbol N and subshell is the symbol L. And so shell number 1 only has one subshell, and it's given this symbol S, which we'll look at a little later. Shell number 2 is 2 subshells, an S and a P. Shell number 3 has 3 subshells, S and P and D. And shell number 4 has 4 subshells. You see the pattern here, S and P and D and F. And you see that as we go up here, this is increasing in energy. The S's are always the lowest one within the shell, and then P are higher, and D are higher still, and F is the highest one. And the final thing that you notice here is that sometimes the energy values overlap. So this 4s level here is of lower energy than the 3d. And so we'll address that a little later too. So remember that the shell number refers to which layer it's on. And these letters here are going to refer to the different energies that are possible. All right, so let's learn a little bit more about that. Okay, so let's break down a little further all those possibilities for subshells. First of all, the number. So each shell has the same number of subshells as its number. So shell number 1, which is N, number 1, has 1 subshell. And shell number 2 has 2 subshells, and shell number 3 has 3 subshells, and shell number 4 has 4. And shell number 5 theoretically could have 5, but we never need to go past 4 to do all of the atoms on our periodic table. Now these different subshells are given values starting at the number 0. So that one subshell has the value of 0. I'm not sure why, something to do with that wave equation, which I don't fully understand. I've never used it for anything. But there you go. You're going to label it with the number of 0. And then we have subshell number 2 has, shell number 2 has 2 subshells, and it's going to be a 0 and a 1. And shell number 3 has 3 subshells. It's going to be a 0, a 1, and a 2. And 4 is going to have 4 subshells, 0, 1, 2, and 3. Now, these numbers are not used that often, sometimes, but not as often as their letter designations. And so they're given letter designations that apparently were assigned way back in the beginning when they were studying the emission spectra of hydrogen. And so the emission spectra of hydrogen has these 4 lines, and so each one of them goes with a particular subshell. And so the first lowest energy shell is given the symbol S, and then P for the second one, and D for the third one, and F for the fourth one. So all these zeros, those are S subshells. And then when there's a 1, that's a P. And then when there's a 2, that's a D. And then where there's a 3, it's S, P, D, and F. And again, we don't have to go past 4. Thankfully, that'll do all the elements on the periodic table. Okay, so now we got all these shells and subshell possibilities. Now it comes down to putting electrons into them. And so putting electrons into them follows a particular pattern from low energy to high energy that's called the Albow Principle. And so this Albow Principle of low energy to high energy follows a neat little pattern that I can recreate here with this little diagram. So first off, we have these shells. And then down here, these are all the subshells. And so there you go. Shell number 1 only has S. Shell number 2 has S and P, and so forth. And then the order in which they fill follows this wavy pattern. So if you fill up shell number 1, subshell S, then you're going to go around and come back here and do shell number 2, subshell S. And then you're going to go back down here and do shell number 2, subshell P. And then up to here, shell number 3, subshell S. And then back to the beginning, shell number 3, subshell P. And then 4S. And then back to the beginning here. And you do 3D and 4P. And then 5S. And then back to the beginning. And then 4D and 5P. And then 6S. And then all the way down here, and then 4F, and then 5D, 6P, 7S, and then to finish it all off, 5F, 6D, and then 7P. So that little squiggly line represents increasing amounts of energy. So 1S is the lowest energy, and then 2S, and then 2P, and then 3S, and then 3P, and then 4S, and then 3D, and so forth. And so this energy pattern will become more important later on as we assign values off our periodic table, but this is the pattern, the way to follow it. Alrighty, so we're almost to the point where we can start building the electrons around the atom with our new quantum concept of electrons. The last thing to include here is these new shapes of these electron wave patterns. So as mentioned, the different subshells, there's 4 of them, are of different energies, and so they're going to have different patterns. You can think of them like different apple trees that are dropping their apples in different probability patterns. The first one is a nice, easy to understand spherical shape. It has 1 lobe. And it contains 2 electrons, well, maximum 2. So you can have 1 or 2 electrons in there with that energy, and takes that nice spherical shape around the nucleus. The second one has this sort of double lobe shape where there's a lobe on either side of the nucleus, and so 2 lobes. And there are 6 possible electrons that can have that wave pattern. The d orbitals tend to have this sort of 4-leaf clover shape with the nucleus in the middle there. So that's 4 lobes. And there are 10 electrons that can have that wave pattern. And finally, we end up with the F subshell, which are even smaller. Well, smaller lobes, but more of them. So 6 lobes in most of these wave patterns, and there are 14 possible electrons in each one of these subshells. So the lobes might play a part later on when we start talking about bonding and hybridization, but for now, just have it in your head the idea that there's different shaped lobes for different energy patterns, and there's different numbers of electrons that can have that pattern. So the pattern goes like 2, 6, then 10, then 14. And so now we're going to use that to put together what's called an electron configuration. Alrighty, so now we're all set. We've got the order in which we're going to fill up these different shells from low to high. That's called the Albow Principle. And we know how many electrons maximum can go into each of these subshells. It was 2, then 6, then 10, and then 14. So an electron configuration shows the number of electrons in each subshell starting from the lowest. So it always starts at 1s, which is our lowest. That's our starting point for all atoms. Nitrogen has 7 total electrons, so 2 of them are going to go into that first shell, and then or subshell, then it's going to be full. Then we follow the squiggly line, and it gets to 2s. We put 2 more in there. We've used up 4. There are 3 to go. After 2s, we go to 2p. We add the 3 more in there, and that completes our electron configuration. So let's try sodium. Sodium has 11 electrons. We'll start at the beginning again, 1s2, then 2s2, that's 4, 2p. P holds up to 6 electrons, so we can put all 6 in there, and that makes 10. 6, 2, 2 makes 10, which means our next on our destination here is 3s, and only 1 in there takes us to 11. Our final example here for filling up these different subshells is cobalt. We're going to start at the beginning, 1s2, 2s2, 2p6. There's 10 electrons. Then we go to 3s, going to fill that up. We're up to 12. After 3s, we're going to go to 3p. That's 6 there. And then we're going to go to 4s. 2. We're up to 20 now. 7 electrons left. After 4s goes back down to 3d, so our first time in the d subshell, and we have 10 possible in there. If we're at 20 electrons, we only need 7 more, and so the 3d subshell will only have 7 of a possible 10 in there. So there you go, electron configurations. Now, that little squiggly line is a bit of a pain to memorize, and a periodic table is something you'll always have in a chemistry exam or a chemistry test or anything chemistry you want to do. So I'm going to show you how to use the periodic table to get all of those electron configurations. It turns out that the periodic table is broken down and organized by the different subshell blocks. And you can kind of see by the number of columns which part of the periodic table goes with which subshell. So these first 2 columns here, that's called our S block. And all the atoms in those first 2 columns have their outermost electrons in the S subshell. Now, helium actually belongs over there as far as blocks go, so we'll stick it in there just honorarily for today. The P subshell, if you remember, has 6 valence electrons, or 6 electrons it can hold. And all of these atoms from boron across to neon and then down, it's kind of hard to draw on this, these 6 columns here, that's your P block, right? S block over here, P block there. D can hold up to 10 electrons, and if you count from 3 to 12, that's 10. And so this section here is our P block, sorry, not P, D block. And the last one here is our F block, and the only part of the periodic table that's not already outlined is this bottom section, our lanthanides and actinides. And if you count those across, you should get 14. Actually, maybe 15, depends where they put these elements. Right, so there you go. You got S, P, D, and F, and we can use this in order to come up with our electron configurations without having to use the squiggly line. If you like the squiggly line and want to reproduce it, great, go for it. But I think once you see this and you've done it a few times, you'll find this a lot more handy because you have your periodic table around and are more familiar with it. Alrighty, let's give it a try. So we'll do fluorine using our method using the periodic table. There's fluorine right there. It has 9 electrons. And what we can do is we can always start at the beginning here where hydrogen is 1s. 1s1, and helium be 1s2, so that fills it to that point, right? Then we go down here to level 2, and this is 2s. So 2s1 and 2s2, that's lithium and beryllium. Then we enter the 2p block here, and so 2p. You can see we've used 4, which means we need 5 more. And you can kind of see by counting here, 1, 2, 3, 4, 5. Fluorine's the 5th element in that block. And so you put a 5 there and you're done. Now, you're going to see that these are going to get a bit long and tedious. And what we're going to do is we're going to simplify it a little bit by only going from the configuration after a noble gas, right? So the noble gas before fluorine is helium. And so to abbreviate this one, it's not much of an abbreviation, but you can put the symbol for helium in a square bracket and then just do the parts that come after helium on the periodic table. So this is the 2s block here, 1s up at the top. And so you just start there at 2s after helium and go from there. All right, vanadium. Vanadium, there it is down there. It's number 23. And so we get 23 electrons that we're going to organize into a configuration. So we'll do the long way first. We'll start at 1s again. So that's hydrogen and helium. And then we do lithium and beryllium. That's 2s2. And then boron across the neon. That's 2p. So that's 2p6. And then down here it says 3s. Magnesium and sodium. 3s2. And then we go over here, aluminum across to argon, that's 3p, so 3p6. And then back here to potassium and calcium, that's 4s, so 4s2. And then vanadium is partway through this 3d block. Now remember that the D block starts at the 3rd shell because the other shells don't have a D block. So this is 3D, and then you just count over 1, 2, 3, and there's vanadium. Now to make the abbreviation for that, you just go backwards until you get to the nearest P here. So this whole thing here is the configuration for argon, which is the nearest noble gas before vanadium. So if you go backwards from vanadium, you get to argon, there it is. So we can put the argon into the square brackets, and then the abbreviation is just 4s2, 3d3. So that's a lot easier when you're dealing with some bigger elements on the periodic table. All right, let's try tin. So tin is way down here on the periodic table. It's got 50, looks like, electrons in there. And so you start it just the same way. It's going to be 1s2, and then 2s2, and then 2p6, and then 3s2, 3p6, then 4s2, and then 3d10. Now 3d10 takes us to zinc here. After that is 4p here, which goes across to krypton. So 4p6 gets us to here, to krypton. And then we're going to go down here, rubidium, strontium, so that's 5s there. So 5s2. Then we're going to do the 4d section. Now someone told me that this 4d section is where most of the elements that start with the number 40 are. So that's kind of a neat reference for you, since it's sometimes a place where people get a bit lost. So that'll take us across to cadmium there, 4d10. And then we need 2 more from this 5p block. 5p with 2 more takes us right to 10. Great, that's a long electron configuration. Let's abbreviate it. The nearest noble gas beforehand is good old krypton, so we'll put krypton into the square brackets, and then that takes us up to here. This whole thing here is the krypton, and then after that, 5s2, my bad, and then 4d10 and 5p2. There you go. I hope you get some practice in on that, but once you get the hang of using your periodic table, it should come pretty easy. All right, hope that helped. Take care. See you soon.